Right. So for this module, we already covered the control volume analysis, the first one, conservation of mass. We already concluded this this section already. Yeah. So the mass in will equal to mass out, or m dot equal to m dot in equal to m dot out. Today we're going to look at these 2 weeks, this week and maybe another two more sessions. We will look at the second item here, which is the Newton's second law of motion, which is F equal to ma, or we will deal with momentum. Right? We deal with momentum, and we deal with torque also. So in the following few more slides later on, you will see that we are focusing on no longer focusing on m dot, but we will look at second Newton law of motion, where we will look at force and torque or moment, a twisting moment that happened inside the system. Okay, so you will be hearing forces, moment of momentum, or MOM, for the new for a few more slides later on. Okay, all right. Then, yeah, the rest will follow after we clear Newton's second law of motion. Okay, we start with second law of motion, and this one will be the questions similar to your tutorial chapter 2, question 17. Yeah, question 17. So we would need to define what is Newton's second law of motion. So we start with time rate of change of linear momentum will be the sum of external force acting on the system. So if you put mathematics model, I think is more easier for us to memorize the relationship in a second Newton law by mathematic model. So if you look at your screen, this is the first equation for today. We will take d over dt, the change of rate over time of an integration of the system. And you see this one is v, this one is a v with something in the middle. So this one is the velocity times the rho times the volume, okay, equal to the force inside the system. Okay, so this is the equation. If the question asks you to analyze a control volume using second Newton law of motion, so this is the equation that you need to write on your answer sheet. Okay, this is the first equation we expected in your answer. Okay, you need to define all the sum of all the force will equal to the integration of volume, velocity times density times the volume, then divide by time. Okay. So the first, the integration here, right? The integration here, integration of system. If you take your rho, right? Your rho times volume, rho times volume, you'll get mass. Okay, rho times volume, you'll get mass. Mass times velocity, you'll get momentum. Okay, so recall what you learned in physics. Momentum will equal to mass velocity, mv, right? Momentum will equal to mv. And how you get your mass, if you learn about the fluid mechanics, we will always link with, usually the mass will not be so direct in our system. So we will use rho with its density times the volume to get the mass, because we can measure volume, and times the velocity. Okay. So and then sometimes the volume itself. Let's say we have a cube. We want to calculate the volume. So normally we will have the area times the height, right? Like what we've seen in our previous example. To calculate the velocity, the volume, we need to take the area times the height of the volume. So normally the volume itself will give you A times H times V. Okay, so these are the parameters that you need to be careful when it comes to calculation. So normally we will reduce it to the more fundamental parameter, for example, area, H, density, and velocity. Okay, so these are the fundamental concept that you need to bring back for this section. However, what is the keyword throughout today that we will keep repeating is that the word momentum. We deal with momentum and the second Newton law. Momentum equal to mv. Remember the pattern of the mathematical model, which is integration of your mass times the mass times momentum. And if you take the momentum divided by t, then you will get force. Okay, now how do we define, we know that, how do we write or how do we prove that this equation is valid to carry forward? You know that from second Newton law that you learn in your secondary school, you know that second Newton law equal to F equal to ma, mass times acceleration, right? Now, how do you calculate acceleration? Acceleration is velocity divided by time. Okay. Now, if you compare this format and this format, okay, or this equation, it will be same, right? So when you combine, if you take mass times velocity divided by time, you will get force. So same with this equation. So when you take momentum divided by time, you'll get force. Yeah. So make sure you clear what we're discussing so far. We are recalling what you learned in the previous module, or even some you learned in your secondary school. It is the second Newton law fundamental definition. We deal with acceleration, F equal to ma, and you break the acceleration in terms of velocity divided by time. Then you combine the products of mass times the acceleration, you will get mv divided by t. And mv, mass times velocity, you'll get momentum. So when you read the mathematics equation here, momentum divided by time, if you put in the wording, it will call time rate of change. Time rate of change means divided by t of the linear momentum, which is your mv, will equal to all the force inside this acting on the system. And this one we deal with external forces. Okay, so make sure you understand what we cover so far. Okay, so as long as you understand this principle, you manage to solve question using Newton's second law of motion. Okay. Now, all this you can read from the slides, right? So I will just continue. So I'm showing you a new diagram on the left hand side lower corner of your screen. So what you're seeing here is what we already seeing in the previously. You have a volume in a solid line, and to analyze the control volume analysis method, we will create a dashed line that we label as control volume. So the solid line, normally known as system, and the control volume is what we are interested to know, what is happening inside this domain. We call it domain, inside this control volume. And because we are deal with forces, so the forces will always acting on the surface, okay, acting on the surface. So all this you can read from the slides here, okay. So this diagram is important for this section when we want to derive the linear momentum equation. Now what we are trying to do with this diagram, we're going to derive this equation. Then this equation is called linear momentum equation using this diagram. Okay. All right. Now recall what we covered in the previous slides. All the force will equal to, again, recall. If you cannot recall in exam, just think back what is the definition of second Newton law. F equal to ma equal to mass. Further elaborate about the acceleration is the velocity divided by time. And you know that this chapter deal with momentum. Okay, so momentum divided by time. Okay, so all the force equal to system will equal to all the force inside the content in the control volume. Okay, so this is the first equation that deal with this diagram. Then we will continue. So I will just give you the control volume equation for fixed and non-deforming case again. Under linear momentum equation, we are now look at linear momentum equation. No longer look at the equation previously. The equation previously is the conservation of mass, which is the m dot. This is already done. Now we are dealing with momentum, which is mv. Okay, so don't confuse with our previous equation. All right, now we deal with mv. So again, we call the Reynox transport theorem to derive the equation when we try to solve a control volume, and we look at the first scenario when our control volume is fixed and non-deforming. So later we look at another two more scenario where we will have fixed and we will look at moving and non-deforming, and also we will look at moving and deforming control volume. So we start with the fixed and non-deforming equation. So on the left hand side of the equation, you will have the system equation, where as default you will see that we are taking velocity times rho times volume, and you know that rho times volume will give you m times v will give you momentum divided by time, momentum divided by time will give you the rate of change of momentum. Okay, so we will always deal with the rate of change of something in this module. So today we'll look at momentum. And because we are using the control volume, we will also have two dimensions. One is the control volume, like what we've seen in the previous section, when we deal with conservation of mass. In today's lesson, we will deal with momentum, we will deal with control volume also, and we will deal with control surfaces. Same, however, the content inside the equation here will be different, because again we are dealing with momentum. Okay, so to calculate momentum, we need, for the first component in the equation here or on the screen, you will see we will take rho times v times velocity divided by time. Again, rho times volume, you get mass times v, you get momentum divided by t, you get rate of change of momentum. Then here, the control surfaces today is a little bit different from the previous one. So we will have velocity, rho, velocity. This one is a vector. This is a vector. And dA. Okay. So control surfaces always deal with the arrow that we always talking about. That the one that I always show you. You draw the surfaces, you draw the V, you draw the A, then see whether the arrow is the same and so on. Okay, so this one they deal with the surfaces. Okay, so this is how it works. So of course, if you time this one, V times V times rho times dA, you will still get momentum. You will still get mv divided by time. Okay, you will still get the same dimension at the previous one. The whole equation, we are dealing with momentum, the rate of change of momentum, meaning we take momentum mv divided by time for the left hand side and right hand side. Okay, so today the equation are a little bit different from the previous one. Today we deal with momentum, mv divided by time. So we deal with v, rho, and volume. V, velocity, rho, density, volume, and this one is volume, density, velocity vector times A. The product of this 1, 2, 3, 4 will also give you mv divided by t dimension. Okay, all right. So make sure this equation also important. When you see the question asks you to solve the question using linear momentum equation, meaning we're expecting you to write the whole equation in your answer sheet. Okay. Okay. All this you see on the screen here is just a note for what is represented by this term, and this term. So we know that when we have a control volume that is fixed and non-deforming, you can equal what is happening in the control volume and the control surfaces will equal to all the force that acting on the control volume. Okay, so because in the first slides that we see today, we already proved F equal to mv divided by t. So if you put this equation in these slides, you will see that this 2 actually is the mv divided by t. Right hand side, this one is the force. Okay, this chapter or this section will deal with force and momentum. This is the whole thing is called linear momentum equation when we put force inside the control volume plus control surfaces equation. Okay, yeah. So in your answer, in your test answer, when the question asks you to solve using linear momentum equation, what we expected is that you can write this one or write this one. Okay, but most of the time when we deal with linear momentum equation, we will use this equation instead because it will help us to lock our target answer on solving the force and solving the what is happening in our control volume and control surfaces. Okay, so just to a short conclusion for this equation is that when you are told to use linear momentum equation, write this equation in your answer sheet, you will get 1 to 2 marks. All right, 1 to 2 marks just to write out this equation to show that you understand what is linear momentum equation. Okay, yeah. Okay, to cut short the module time because we have a few more approach that we will need to cover. So in this module, just for info, we will not considering deforming control volume and accelerating control volume. Okay, yeah. So just take note lah. So for linear momentum equation, we'll just look at a fixed and deforming control volume, non-deforming control volume. So there's only one equation that you need to worry about. when it comes to linear momentum equation. We did this one. This is the only equation that you need to know where to use this one. Okay, so continue with what we covered so far. So far, we still focusing on the equation, the momentum, the rate of change of momentum, which is the second Newton law, which is what is happening in the control surfaces, control volume and control surfaces will equal to the force acting on the control volume. So let's look at the diagram on the right-hand side of your screen. So you have the flowing from below and then come up from above. So you have flow in and flow out. And then you draw the control volume, the area that we're interested in, the control volume. Then you enlarge, you look at what is happening inside the control volume. So if you look at the free body diagram that is on your screen on the lower left corner, so you will see that how you sketch the control volume. First, you trace the shape of the area that you are interested in. So you trace the shape. This is step number 1. Then after that, step number 2, you focus on the fluid itself. Okay, you focus on the fluid. This is step number 2. So you will have a fluid acting, and we focus on the force. Again, this section we are looking at force. So force. So fluid will go in this. There's a force at the bottom, and there's a force on the top, which is pointing in to the area. You see, all the force is pointing. If you have a control surfaces, for this section, it's very easy. All the force always pointing to the dash control volume. All the force that you have for this section, for this second Newton law, that when you want to solve the force on the right hand side in the equation, remember when you draw the free body diagram for the control volume, all the force will always pointing to the dash line, like this one. So you see the flow in and out, and there is a force at the wall there. So you see the force at the wall, you will have pointing in to the wall, and there's an arrow pointing along the wall. So there are 2 directions of the force of the wall. And also we need to consider the fluid weight. We need to consider the third thing, because we live on Earth, we have something called gravity. Okay, gravity is the one that gives your mass converted into something physics, we call it weight, W. So for this module, be careful when you look at mass and W. It will be different entity or parameter when you define it in your answer. So if you want to calculate weight, normally we'll take the mass times gravitational acceleration. And just a highlight, for this module, since you're in the 3rd year already, your gravity value, if it's not given in the question, we will use 9.81. If you use G to 10, I'll give you wrong answer, because 10 is not the accurate calculation when it comes to control volume, especially when you calculate something happen on Earth. If you use 10, it will not give you the correct, you will oversimplify the problems. Then you might damage the instrument, or you might, if it's happened to the end user, then you might hurt somebody because you oversimplified your calculation. Okay, so again, for this module, the gravity, although the gravity acceleration, although it's not mentioned in the question, use 9.81 as your calculation. Okay, now for some of the tutorial that we will discuss throughout the module, sometimes we will simplify case just to show you the concept how we apply the equation. Sometimes you will see G equal to 10. Just to let you know. Sometimes the tutorial will use G equal to 10. However, for your test or final exam, or even when you go to work later on, please use 9.81 in your calculation. All right. So far we're still at the surface of how to use this equation. Okay. So the force, we will look at what happened to the body and surface forces. We already covered what happened to the gravity when it happened on Earth. So something we'll call weight. Something will happen to your mass under the effect of gravity. We call it weight. And we will have reaction surface force. That what you see at the lower left corner here. Okay. So far we still deal with individual equation, which is what happened to your control surface volume plus what happened to your control surfaces will equal to forces acting on the control volume. We are dealing with force and momentum now. Force and the rate of change of momentum, which is mv divided by t will give you force. We're still repeating F equal to ma relationship. It's just that we expand it a little bit to solve control volume question. A few important idea or principle that we need to be careful when we use the linear momentum equation. It is this one that we keep repeating since the beginning of this lecture. The first one will be we will have the flow to be uniform. Okay, once you see the word uniform flow in the question, you can simplify the equation above, especially when it comes to integration steps. Okay. Right, so this is the first one. So when the flow is uniform, or the statement mentioned the flow is uniformly flow into the vessel or something, then you can simplify the integration process. Then be careful on the linear momentum, which is your mv. It is a directional. Why? Because if you look at the second term here, we deal with the vector. If you study vector, vector is something that having magnitude plus direction. Okay, direction. So be careful when you do calculation for this section. When you deal with linear momentum equation, just remind yourself that we need to take care of this section, which is deal with control surfaces, which is v dot n hat, which is a vector form. So you have a positive negative when you do calculation. Now most of the error will happen here when it comes to test or final exam. Okay, if you don't understand the direction, then you will snowballing to the final answer. Okay, so just take care of the direction. I'm going to explain the direction later on. Okay. Third one. Okay, I'm going to show you the diagram now about the direction. Okay, so if you look at the diagram that on your screen, where if you already download the tutorial from the Moodle, this diagram can be found in question 21. Question 21 will give you this diagram that you see on your screen on the left-hand side. If let's say you have a solid line and the control volume is the same as the shape of this shape. So what mean by this statement? What mean by this number 3 statement here? So the first thing is that you need to look at what is your inlet, what is your outlet. Yeah. So before you start solving a question, you need to look at where is the inlet, where is the outlet. So I will highlight with the yellow dash box that you see on your screen here. When you look at bottom, this one, if the flow is inlet, which is go into the control volume, we will define the momentum. We are at momentum section. MV for inlet or into, we will use negative. We will use negative. This one will give you negative value if it is an inlet. No matter whether you have a on the you see the notation, this equation, v rho v dot n hat less than 0, it means that it's negative. What mean by v rho v dot n hat? This one is your linear momentum. This one, the whole products for your control surfaces. It will when you have an inlet, your linear momentum will become negative value. So if you can see the blue color here, if you take the velocity times the n hat, you'll get a positive momentum. If you take this n arrow times this v arrow, you'll get negative. So no matter whether your linear momentum, is positive or negative, at the inlet, the products that you will get for this section, for the second section of the equation, which is deal with the control surfaces, when you deal with inlet, okay, no matter the linear momentum, whether it's positive or negative, so it will give you the negative answer. It will give you a negative answer for the whole products. Yeah, if you have an inlet, no matter it's positive or negative, your linear momentum, it doesn't matter. It will give you the end products of v rho v dot n hat will less than 0. Will give you a negative value. Okay. Now in test, how this going to apply in your test? If your answer, after you calculate v rho v n hat dA, you get, let's say, negative 1000. This one represent the momentum, the red momentum, represent mv divided by t. So if you get a negative, it just means that you are calculating the flow is flow into. It just mean you just need to explain when you get negative, what does it mean? It just means that the flow is going into control volume. Means it's an inlet. You let some flow or fluid flow into the control volume when you get a negative answer. Okay, yeah? Try to understand what we are covering so far. This is an important concept. If you don't understand, you will make a lot of mistakes later on. Okay. So make sure you understand what is this statement number 3 here on the screen. What does it mean? When you have an inlet, no matter what is the arrow pointing in or out, you will get a negative number for end products. Okay. If you get a negative, if you see it is the inlet, then this whole thing will get a negative value. And if you have an outlet, you apply the similar understanding. If you have an outlet, no matter you have a negative linear momentum or positive linear momentum, if you are referring to outlet, you will get a positive sign of the product. If you can see the diagram, the V rho V dot n hat more than 0 means it's a positive value. What does it mean? Is that if you're having a system, let's say I'm drawing the control volume, and the flow is flowing in from 1, flowing out at 2. If you calculate this section called control surfaces, we are expecting that you have negative something, negative A, which is the linear momentum that go into section 1. Come out section 2, you will have a positive B value in your answer. Meaning for this section, when you do calculation later on, if you have 2, then you have a negative something for linear momentum go into the section 1. If you have outlet, if the fluid is coming out from one of the outlet, then you get a positive. Okay. Now, if you have 2 outlets, if your control volume have 2 outlets, okay, let me change the color so you can see the differences. So if you have 1 inlet and 2 outlet, let's say I label this one as A, this one is B, this one is C. And if you calculate this section in your answer, it's going to give you we are expecting that the linear moment for inlet will be positive air value. A is a linear momentum. You calculate rho V rho V dot n hat dA, you get the value of A plus. And since you see B and C is an outlet, so no matter how you calculate it, make sure in your calculation later on, you check your answer, the B in front of the B linear momentum, or when you calculate the V rho V dot dA dA at this section, make sure you put a negative sign in front, the B. For C also is an outlet, so you get a negative C value. Okay, so expect to get this kind of answer when you come to your answer sheet later on. Okay, so I've done explaining the statement number 3 here. So just be careful when it comes to inlet and outlet. And when you solve question, always look for coordinate reference axis, your X and Y. So for example, if you look at the diagram on the left hand side, X positive is going to the left. Y is positive when it's going up. Okay, so for linear momentum equation, we will deal with coordinate direction, which is the first one. Second one, we deal with flow. Okay, which is your V. Okay, if the V, the flow is flow into, let's say you have a vessel. If the flow into, you get negative sign. If the flow out, you get positive sign for the flow. So you have 2 important entity here. One is flow, one is coordinate direction, which is linked with the coordinate here. Okay. So you will take some time to digest what is happening on this diagram and how it affects your control surfaces dimension or calculation for this component. Okay, because this is the component that link with your vector. Okay. The fourth one, a few more slides, then we go for a break. So the fourth idea is that for a non-deforming control volume, if you see a steady flow in the question, straight away, this section, quickly go and draw an arrow, right steady below or around the arrow. This whole thing equal 0. You'll get marks for the arrow, the notation steady equal 0. You'll get 1 mark for understanding what happened to the steady flow. What will this steady flow affect the linear momentum equation? Okay, so be careful. There are some keyword that will give you some free point or free marks or bonus mark to score. So when you look at steady flow, then something will happen to this one. And be careful, we are looking at this one, non-deforming. When it's non-deforming, then only steady flow works in this way. Okay, we're done with steady flow, equals 0. Number 5, make sure the control surfaces that you draw is perpendicular to the flow. What does it mean? So if you look at the diagram on the right hand side, the control surfaces, the control surfaces that you pick, the dashed line, you will see that the flow will always perpendicular to the area. For example, the inlet and outlet. Okay, the V in or the pressure or area will always 90 degree when you do analysis. Same with this one. The velocity will always 90 degree to the dashed line here. Dashed line, especially this area. Okay, it will 90 degree. Okay, same with okay. So again, we are focusing on force. So you know that pressure equal to force divided by area. So always rewrite or rearrange the equation in terms of force. So force, we will take pressure times area. So again, pressure will be given in the question. Area will be given by the question. So remember, these two will help you to find your force. Pressure times area get force. Just be careful on the section that you're looking at, whether they are inlet or outlet. Yeah. So statement number 5, 90 degree. What is 90 degree? The velocity, pressure, and area always 90 degree, especially the pressure. Pressure and the volume, not volume, velocity. Pressure and velocity will always 90 degree. When you draw the diagram, make sure you draw it properly. Okay, so the sketching also have some marks in the test. So when the question asks you to show or to sketch the control surfaces with all the forces, for example, forces, it means pressure and velocity and so on. Make sure you draw it 90 degree to the inlet and outlet. Okay. And again, force in this section always pointing to the surfaces. When you draw force, as you can see on the diagram here, the red color arrow always point to the surface, pointing to the surface. So we all used to the inlet and outlet, so just be careful. Don't confuse with the velocity, the Q, and so on. So be careful. When we deal with force, the force always pointing to the area, or to the control surfaces. Okay, I think we deal with the. Okay, other thing is just we will cover when it comes to example. For example, atmospheric pressure, what we do, sometimes we need to consider, sometimes we don't need. It depends on scenario. And sometimes we can cancel out. I will give you the example. Okay, and the external forces, the F, will have a positive and negative sign. And this one, the forces will refer to your reference axis, X and Y. So if the force is along x-axis, positive. If the force going up, it's positive. If the force going to the left, then negative. The force going down, negative. This axis, you need to look at the diagram. Sometimes I will be a little bit tricky when it comes to exam. I will draw the axis like this way. It means your positive will go to the right for X. However, your Y will be positive going down. Okay, you have to be careful on the axis given in the question. It is not necessary this way. You have to refer to what is given in the question. So sometimes I will put this one in the diagram. So be careful to look for this reference axis. This one is to solve the force. Okay. What else? Okay, the rest you can read from the slides. External force, force. Okay, so this one you can read. Okay, I think we stop here, then go for a short break. Okay, so again, point number 8 and 9, you read from the slides. Stop the recording.